In the previous two videos, we did two different types of calorimetry problems. This is the third type you will encounter in the class. It is when a substance, the same substance, can undergo multiple phase change and or temperature change. So if I look at my heating curve here, whenever it is horizontal line or a plateau, flat line, no, there is no temperature change. So our equation becomes Q is equal to MHF, the heat of fusion, or Q is equal to MHV, which is the heat of vaporization. Every single time there is a diagonal line, that means there is a temperature change, and we must modify the equation to Q equals MC delta T. In this type of problem, every single time there is a slope change, you must use a new equation because the heat constant for a solid is different from the C constant of a liquid as well as for steam. The heat of fusion for an object is different from the heat of vaporization. So whenever they go to multiple phase change or temperature change, depending on where they are located, more than one equation will be used. So here is the heating curve of water. You guys know the vertical axis is temperature or average kinetic energy. The horizontal is heat or potential energy or time. The first flat line or plateau is 0 degrees Celsius of water. This is where the water melts or freezes. The second horizontal line or plateau is where the boiling point occurs. So vaporization and condensation occurs. Anything below 0 degrees Celsius is a solid state. And there's a temperature change, so we use Q equals MC delta T, as noted in the previous slide. Between 0 degrees Celsius and 100 degrees Celsius is liquid state, and the C constant for liquid is different. Since there is a temperature change, we again use Q equals MC delta T. Anything above 100 degrees Celsius is going to be in the gas state. Since there is still a temperature change, we use Q is equal to MC delta T. Another important thing to note is this point right here is 0 degrees Celsius ice. At the end of the melting line is 0 degrees water. They're at the same temperature, but different states of matter. On top, the beginning part of vaporization or the ending part of condensation is 100 degrees Celsius water. On the opposite end, when vaporization is completed or condensation is starting, is 100 degrees Celsius steam. How do you know this is the third type of problem? It will always be the same substance. It will undergo multiple temperature change or phase change. When you have something like this, the first thing you want to do is sketch a heating or cooling curve. It does not have to be detailed, just a sketch. In addition, you want to mark the starting and stopping point. This will help you figure out how many equations you need to use to solve this problem. So calculate the heat required to change 50 grams of water at 25 degrees Celsius to steam at 100 degrees Celsius. So we know this is a type 3 problem because it is one substance, which is water, and is undergoing multiple temperature changes. So the first thing you want to do is draw a sketch. The lower portion is 0 degrees Celsius. The upper portion is 100 degrees Celsius. After we draw the sketch, we're going to mark the starting and stopping point. The water is starting at 25 degrees Celsius, which is down here, and is ending at 120 degrees, which is up here. The easiest way to determine the number of equations used is look at the change in slope. Every single time the slope changes, you must use a new equation. For this problem, we're going to use 3 different equations because there's a slope change here to here and then to here. So the first equation we're going to use is going to be between temperatures 25 degrees Celsius to 100 degrees Celsius. The reason we stop at 100 degrees Celsius is because between 25 degrees to 100 degrees, you are at the liquid state. A liquid state and a gas state have different heat constants, so you cannot mix them together. Whenever there's a temperature change, we know the equation is Q is equal to mc delta T, in which delta T is T final minus T initial. Now I'm going to plug in. The mass given is 50 grams. Since we are in the liquid state, the C that we're going to use is for liquid, which is 4.184 joules per gram degrees Celsius. Since it went from 25 degrees Celsius to 100 degrees Celsius, my final temperature is 100 degrees Celsius minus 25 degrees Celsius. 100 minus 25 is 75 times 4.184 times 50 will give you approximately 15,700 joules. We went from right here, which was 25, to 100 degrees. Now we are at the vaporization point. When an object or substance is vaporizing, we know there is no temperature change. At 100 degrees for water, since there's no temperature change, the formula becomes Q is equal to mHV. My mass is still the same because it's the same substance undergoing the change. My heat of vaporization is given right here as 2,260 joules per gram. We multiply the two numbers, and that is going to be 113,000 joules. After we vaporize, we are at this location, but the steam is still being heated, so it raises its temperature to 120. At that point, we are going from 100 degrees steam to a higher temperature, which is 120 degrees steam. Since there is a temperature change, the equation we're going to use again is going to be Q is equal to mc delta T. Since the substance is the same, the mass is going to remain the same. It's going to be 50 grams. The C provided, since we are at gas, is going to be 2.02 joules per gram degrees Celsius. My final temperature is 120 because I'm stopping at 120 degrees minus my initial temperature, which is 100 degrees Celsius. That is where the steam is starting. So we do the parentheses work first. 120 minus 100 times 2.02 times 50, and that will give you 2010 joules. So to find the heat required for this entire process, I need to add the 3. So Q total is going to equal to 15,700 joules plus 113,000 joules plus 2010 joules, which equals to 1.30 times 10 to the 5th joules. Pause the video and try this problem on your own and then check your answer. Here, we're going to determine the energy required to cool 200 grams of water from 125 degrees Celsius to 25 degrees Celsius. It is the same substance going through multiple changes. First thing we're going to do is sketch a graph. Bottom plateau is 0 degrees Celsius for water. The second one is 100 degrees Celsius for water. Next, I'm going to mark the starting point, which is 125 up here, and we are going to 25. There are 3 different slopes. There's 3 different equations. So we're going to start from the top, and then we're going to cool it by condensing it, and then we're going to cool it even more by lowering the temperature. So this problem also has 3 equations. First one we're going to start with is from 125 degrees Celsius to 100 degrees Celsius. It is only a gas at this point, so we have to stop at 100 degrees Celsius. Since there's a temperature change, it's going to be Q is equal to mc delta T, and it is going to be T final minus T initial. So my mass is going to be 200 grams. Since we are starting at steam, we're going to use the steam constant, which is 2.02 joules per gram degrees Celsius. My final temperature here is 100 degrees Celsius because that is where I ended, and my initial temperature is 125 degrees Celsius, and that makes sense. If I'm cooling something, I have to release heat, so it's going to be an exothermic reaction. We do the parentheses work first, so it's 100 minus 125, which will give you a negative 25 times 2.02 times 200. This will equal to 10100 joules. Or next, we have to condense because we're right here. We are at 100 degrees Celsius. When we condense, there is no temperature change. So it's the opposite of vaporization. So it's going to be Q is equal to mHV. My mass stays the same, which is 200 grams. Vaporization is given as 2,260 joules per gram. Calculate the math, 452,000 joules. Now we are here. We complete our vaporization, and now we're bringing the temperature down again. So we are starting at 100 degrees Celsius, and my ending temperature is 25. And we know this is at the liquid state. And since there's a temperature change, we know Q is going to be equal to mc delta T. My mass is still the same because it's the same substance, but between 100 and 25, we are at the liquid state, so this is 4.18 joules per gram degrees Celsius. My final temperature is 25 degrees Celsius minus 100 degrees Celsius. We do the work in the parentheses first. 25 minus 100 is 75 negative times 200 times 4.18, a negative 62,700 joules. And this was also negative because 100 minus 125 was a negative. And that is correct. Why? When you cool, you are releasing energy. It is an exothermic equation. And anything that is exothermic is always going to be negative. However, if you notice, when we were condensing, the math came out positive. Both the mass and the heat of vaporization are positive. So when you are cooling, you must remember to put a negative sign in front. Q total here is going to be negative 101 joules minus 452,000 joules minus 62,700 joules. If you add everything up, negative 524,800 joules. Better way to write this is with scientific notation. So this is going to be negative 5.25 times 10 to the 5th joules. Or you could write it in kilojoules. So please note, when you cool, the answer should come out negative. Your Q equals mc delta T. These equations will always come out negative if you do your temperatures correctly, final minus initial. However, MHV, MHF does not always come out negative. Therefore, you must remember to put this negative sign if it is an exothermic reaction. So in this problem 2, it says how many joules are given off when 120 grams of water are cooled from 25 to negative 25 degrees Celsius. First thing we want to do is we want to draw this little sketch. But this is 0 degrees Celsius. This is 100 degrees Celsius. We're going to start at our starting point, which is a positive 25. And we are going to negative 25. There are 3 slope changes, so there's 3 equations. We have an equation here, we have an equation here, and then we have an equation here. So the first equation we're taking from 25 degrees Celsius to 0 degrees Celsius. Since there's a temperature change, it's going to be Q equals mc delta T. My mass given is 120 grams. My C is liquid, so I have to use 4.18 joules per gram degrees Celsius. My final temperature is 0 degrees Celsius. My initial temperature is 25. So we do the parentheses work first. 0 minus 25 is a negative 25 times 4.18 times 120 is 12,540 joules. Now we are here. We are freezing. Since we are freezing, there is no temperature change. We are at 0 degrees Celsius. So my equation becomes Q is equal to MHF, which is the heat of fusion. Since it's the same substance, this is 120 grams. Heat of fusion is given as 334 joules per gram. This should be a 4. 120 times 334 is approximately 40,080 joules. So now we froze everything, and so now we're getting even more of a solid. We are starting at 0 degrees Celsius, and we are going to negative 25 degrees Celsius. So this is going to be Q is equal to MC delta T because there is a temperature change. My mass is still 120 grams. However, this is a solid, so the constant I'm going to use is 2.05 joules per gram degrees Celsius. It is T final minus initial. T final, my final stopping point, is negative 25 degrees Celsius minus 0 degrees Celsius. So negative 25 minus 0 is negative 25 times 2.05 times 120. The math becomes negative 6,150 joules. And I forgot the negative up here. Again, since this is cooling, if you do your Q equals MC delta T correctly, final minus initial, it will come out negative. However, just like the condensation point, the freezing point, the mass and the heat of fusion are both positive. So when you are cooling, you must put a negative sign in front. Because if not, you're going to end up subtracting the freezing energy, and you don't want to do that. You want to add it. So Q total is going to be the addition of all three numbers, negative, and you could convert these into kilojoules too if it's easier for you. So if I add all of this together, negative 58,770 joules. Better way to write it is scientific notation, so it's negative 5.88 times 10 to the 4th joules, or you could leave it in kilojoules. Pause the video, try this problem on your own, and then check your answer. How many joules of heat are required to heat 75 grams of water from negative 85 to 185? Again, there's multiple temperature changes, so I know I need to draw a sketch. So my bottom one is going to be 0 degrees Celsius. My second plateau is 100 degrees Celsius. Now I'm going to mark my starting point. My starting point starts below 0 at negative 85, and it ends above 100, so it's at 185. So based on the graph, there are 5 slope changes, so there are 5 equations. So we have 1, 2, 3, 4, 5. Remember, each slope has a different constant value. Therefore, you have to write a different equation. So we're going to start from negative 85. So negative 85 degrees Celsius, we can only go to 0 degrees Celsius right here. Since negative 85 to 0 degrees Celsius, the water is at a solid state. Beyond 0 degrees Celsius, you will have both liquid and solid. Therefore, we can only use the first equation to 0 degrees Celsius. Since there's a temperature change, it's going to be Q is equal to MC delta T. And again, delta T is T final minus T initial. My mass is 75 grams. Since it's below 0 degrees, we have to use the solid, which is 2.05 joules per gram degrees Celsius. T final is 0 degrees Celsius minus a minus 85 degrees Celsius. Remember, this is T final minus T initial. My T final is 0 degrees Celsius. Then we have a negative sign, but my initial temperature is a negative 85. So that's a minus and minus. So this is actually adding. So you're going to have a positive 85 times 2.05 times 75. You should get approximately 13,068 joules. We are right here at 0 degrees ice. Now we're going to melt at 0 degrees Celsius. We are melting, so Q is equal to MHF. Same substance, so it's still 75 grams. HF is given as 334 joules per gram. This is equal to 25,050 joules. So we finished melting. So we are here at 0 degrees water, and we have to raise the temperature to 100 degrees water. That is going from 0 degrees Celsius to 100 degrees Celsius. My equation is, again, Q is equal to MC delta T because there is a temperature change. My mass is still the same because it's the same substance. My C now is for the liquid because we are in the liquid phase. So 4.18 joules per gram degrees Celsius is still T final minus T initial. My final temperature is 100 degrees Celsius minus 0 degrees Celsius. You multiply all of this through, you get 31,350 joules. Now we have raised the water temperature here. Now we need to vaporize it to become steam. So at 100 degrees Celsius, there is no temperature change, so it's going to be Q is equal to MHV. My mass is still the same, 75 grams. Heat of fusion is 2,260 joules per gram, 169,500 joules. Now we have produced 100 degrees steam. The steam has to be raised higher in the temperature. So we are going from 100 degrees Celsius steam to 185 degrees Celsius steam. Since there is a temperature change, this is going to be Q is equal to MC delta T. My mass is still the same because it's the same substance, 75 grams. Now we are using the gas constant, which is 2.02 joules per gram degrees Celsius. My final temperature is 185 degrees Celsius minus 100 degrees Celsius. Do the parentheses work first? That's 85 because it's 185 minus 100. And multiply the rest. You should get 12,877 joules. We are going from a solid to steam. We know we are absorbing heat. This is an endothermic process. Therefore, all the numbers should come out positive. So to get the total, we have to add up all the heats. So Q total is going to equal to 13,068 joules plus 25,050 joules plus 31,350 joules plus 169,500 joules plus 12,877 joules. If you add the math correctly, you should get approximately 251,845, or it's better in scientific notation, so it's 2.52 times 10 to the 5th joules, or you could leave it in kilojoules Pause the video and try this problem on your own and then check your answer. So how many joules of heat is required to heat a frozen bottle of ice at 0 degrees Celsius to 100 degrees steam? So we already know there's going to go multiple temperature change. We're going to draw our sketch. The first one is 0 degrees Celsius. The second one is 100 degrees Celsius. We are starting at 0 degrees ice. 0 degrees ice is right here. We're going to go to 100 degrees steam, which is right here. If you don't remember this, go back to the beginning of the video. There are 3 slope changes. So this is 1, 2, 3. So there are 3 equations. The first equation we're going to use is at 0 degrees. So since there's no temperature change, we are melting this. So it's going to be Q is equal to MHF. The mass given is 360 grams. I forgot to type it in, sorry. It's 360 grams times the heat of fusion, which is 334 joules per gram, 120,240 joules. So we melted everything, and now we have to increase the temperature. So we're starting at 0 degrees Celsius and we're going to 100 degrees Celsius. Since there's a temperature change, this is going to be Q is equal to MC delta T. The mass is going to stay the same as 360 grams. Since it's liquid, this is going to be 4.18 joules per gram degrees Celsius. My final, always final minus initial, is going to be 100 degrees Celsius minus 0 degrees Celsius. This is going to equal to 150,480 joules. Raise my water from 0 degrees to 100 degrees. Now I'm going to vaporize it because I want it to become steam. So we are at 100 degrees, so that my equation is going to be Q is equals to MHV because we are vaporizing and there's no change in temperature. My mass is still the same, 360 grams. My heat of vaporization is 2,260 joules per gram. This is going to equal to 813,600 joules. Everything should come out positive because we're going from 0 to 100, so we're adding heat. So this is an endothermic process. To find the total energy, we go Q total, 1,084,320 joules. Again, the better way to write this in scientific notation. So this is going to be 1.084 times 10 to the 6 joules, or you could write this in kilojoules. So these are type 3 problems. It is one substance. They go through multiple changes. Easiest way to figure out how many equations to use, draw your sketch. Every single time there's a slope change, it is a new equation because they have different constant. The heat constant and the heat of fusion and vaporization is different.